I'm going to talk about exchange methods for constrained experimental design. Experimental design is about how to construct an experiment, how to set factors in an experiment. And I'm very glad that Günther Pilz is in the audience, because he will tell you how experimental design saved his life. So it's a life-saving device. I hope I can be more specific about that. So I'm from the Department of Applied Statistics in the Social Economics faculty, and the project team is, I don't have photographs, unfortunately, Eva Benkova, she's in brackets, and I will explain that why that is so soon. Andreas Rappold and Elam Yousefi, unfortunately both of them are not present today. It's holiday season, and we have also external partners on this project, Radoslav Hamann from the Comenius University in Bratislava, and Joachim Kunert from the Technical University of Dortmund. So it's all about experimental design, but as the speaker before me was motivated by nature, or by animals even, we are motivated by animals too, as you've already seen this slide. So in our case, it's chicken. This is a photograph I don't have copyrights for, so don't film it if things are filmed. But anyway, this is from Quantum magazine, and it shows in the eye of the chicken there are these cells in the retina for taking susceptible for light, and they are in different colors. And when you look at the colors separately, these color cells separately, you will notice, for instance, the red ones or the orange ones, and here you see a schematic, that they are placed in a rather regular fashion. And they are placed in a fashion such that is much more uniform that you would expect if the placement was random. Okay, and this is called, this effect of placing it more uniformly as by random allocation due to a uniform distribution is called hyperuniformity. Okay, so this is more uniform than uniform, all right? And this is a very nice feature. It's a good feature for the chicken, probably. I don't know what it does for helping it to see or something. But why is this relevant for experimental design? Think of this as an experimental region where you have two factors, one factor here and one factor here that you can choose. And you take measurements on the combinations of these factors. And you get responses. And you want to cover, of course, your experimental space where you want to get information from as evenly and as uniform as possible. Okay, so these red locations, for instance, would indicate the so-called experimental sign. These are the locations where you have to take your observations, right, to get a uniform coverage of the space. All right, so this in experimental design typically we call space filling property. Okay, so space filling we use as an experimental design principle, and now the question is, how can we achieve space filling? Okay, in 2 dimensions it might seem trivial, but we have typically 3 concepts. That is quasi-random sequences, Sobol and Niederreiter sequences. The latter one is a honorary doctor of this university, so you might know about it. They are, for this purpose, not quite suitable. I will explain in a minute. And then what we term so-called soft and hard space filling techniques, statistical techniques. And what we are particularly interested in are so-called computer simulation experiments. And these are typically high-dimensional and sparse. So you have just very few possible runs, because these computer simulators are very expensive to run and take a lot of time. So you have just a few runs, and you have usually dimensions not 2, but say 10 or 100 or more. Okay, so we want to be space filling in very high dimensional spaces. And quasi-random sequences are not very good at that. Yes, they're quite good in space filling when you have a lot of runs. Yes, so they are asymptotically space filling. And then there is another downside to it, but I'll come to that soon. I will now first show you the two principal approaches, very simple ones. Those are maximin and minimax distance designs. What is the difference here? Maximum distance design is the design points are put in a way such that they maximize the minimum distance between each 2 points. Okay, so this is a 7-point maximum distance design. Here we have a 7-point minimax distance design. Here the maximum distance from any point in the region is minimized with respect to the points in the design. Okay, but both of these things are soft criteria because you have the criterion. We call these soft space filling criteria. You have the criterion, and when you generate the designs, typically by an algorithm that finds you the points, this criterion is in a way optimized in a soft way. You see what the difference is to the hard approach. The hard approach is possibly best explained by those designs here. They are called Latin hypercube designs. Latin hypercube designs are created in the following way. There is a grid that you don't see, a 7x7 grid, which is lying behind, you can imagine. And those design points are at the grid points of this 7x7 point grid. And they are allocated in a way that you have only 1 point in each row and column. Okay, so this is how Latin hypercubes are designed. And of course, the space filling here is hard because you force them to the grid. Yes, so you force the constraints on the designs rather than you let, in a soft way, the criterion be fulfilled. Of course, here you have a little bit of variance, possible variance, because you could, for instance, switch this point. You can move this point down, for instance, here, and this point up. This would still be a valid Latin hypercube design. So you don't have a unique solution, which gives you the opportunity that you, among all the Latin hypercube designs that you have for a specific size, you can select according to a secondary criterion, which is more meaningful, also in a statistical way. And this was proposed by Jones and others in 2014. They called this bridge designs. These designs. So typically, the secondary criterion would be something that relates to the model that you are then estimating or fitting to your data. Okay, and this would be something like a so-called optimal design, which maximizes the determinant of the information matrix that you get from this experiment. But also it could be a space filling criterion as well. Okay, so well, anything that you can combine with these designs. Now we have come up with a concept that we call privacy sets as an operational concept how to generate such designs. And privacy sets, in some sense, unify all these generation methods for hard constraint designs that I told you. For instance, first of all, the concept. So here, when you have a discretized region and you have a single point X that you have selected, then the privacy set is the set from which you are not supposed to select other points from. This is the blue set. So you can define a certain structure for these sets. And in this case, for instance, here, you have the privacy sets look like this. They are like crosses. And of course, this would then lead, when you utilize the privacy set as a concept, to Latin hypercube designs, because you're excluding points that are in the same row in the same column. Okay. Then you can use privacy sets in the following way, so that you exclude for several rows and several columns. This would lead to these rich designs. You can just exclude the point itself. This would lead to so-called replication-free design, so you're not allowed to replicate at the same point as you have taken observations already. And we have covered these three things in a paper in 2016. We have a very nice efficient algorithms for generating designs for any practically any dimension and any number of points. But what was open is designs with privacy sets of this form, which would generate you distance designs, as I showed you before. And they are usually quite nice and useful. So we need something for that setup. Eva Benkova, unfortunately, she did her PhD on that. She had to leave the project because she became pregnant and has given birth since, and she's almost finished with the thesis, and I hope she will be finished soon. So this is part of her PhD thesis project, and she came up with the following thing. Very nice observation that when you want to generate minimum distance designs with privacy sets, I'll give you another example here. So here we have 11 points, here 18 points, and some given setup. Then when you want to find a candidate point for an exchange, sorry, I didn't tell that, exchange algorithms always, add a point and delete another point. So you're exchanging, the algorithm works like exchanging points from the candidate sets to the taken sets, and so on and so on. So you exchange, and you have this Voronoi tessellation, which gives you for each point the set of points that are closest to this point and no other. And the nice thing is that now we have a theorem she has in her thesis that for candidate points you just have to look along the edges. You just have to look at the vertices of these Voronoi cells. Okay, so you don't have to look at all these white points that are eligible points, all points from the white area, but just to look at these blue corner points here. And this is very nice because for this there are very efficient algorithms already available in the literature. So it's very quick to search through these Voronoi points in high dimensions. Okay, there is unfortunately one downside. It's not quite true what I tell you, because obviously you can see that other candidate points that are still useful from these points are the points here. And they are really nasty, yes? So these edge points at the edge of the region, they make trouble. Sometimes they don't, like here, you see, there is no point available, but they need a special treatment which slows down substantially all the algorithms, but that's another issue. Okay, so we have here these minimum distance privacy sets now. We have an algorithm that runs nicely, and I think it's close to finishing this part of the project by completing Eva's thesis. So what were the project goals of our LIT project? To find an efficient exchange algorithm for minimum distance, Latent Hypercube bridge designs. This is achieved. Publicly available software for it, an R package. Eva is working on that, and it should be finished within her what she's still doing for the thesis. And to acquire funding for a follow-up project that concentrates on so-called incremental properties. That is, properties when you don't generate the designs at once before the experiment, but you increment it during the experiment. We were successful in finding funding for this project, Index. It's a joint project of the FWF and the French research agency, Agence Nationale de la Recherche. And it's a joint project with colleagues from the University of Nice. And what are our other goals within the LIT project? Combined with the Index project, okay, we would like to use exchange methods not only for for space filling and model estimation, but also for so-called model discrimination. That is, when you have candidate models and you want to decide which of the models better fits to whatever you observe. Then for multi-response experiments, you don't observe not just one feature but many features, and those features might be correlated amongst each other. That's quite a common thing, and typically you use copular models to do that. So this model discrimination is Elham's task. He's doing that, and the copular part is done by Andreas. And then we have there is another open question is this exploration techniques. That is when you not only want to learn about the models that you are using or fitting, but you also want to optimize results. Okay, so you do both. You explore the space, you explore the model, and then you exploit it to get an optimum solution. So this is what we wanted to do. Here there are a few references, just the main one, and from the beginning. And that's all I wanted to say. Thanks for the attention. I'm open to questions.